Hi everyone, it's Sorkin. Today we are going to take a look at the bigo notation. So first let's define what is a bigo notation. To simplify it, bigo notation is how the time an algorithm takes depends on the size of the input. So basically how the runtime of an algorithm changes depending on the input. So first let's review a scenario when the runtime of an algorithm does not depend on the size of the input. So for that, let's take a function access element, so where we are receiving an array and where we are receiving an index, and we need to return the value of the array in that index, and we are simply just returning array index. So what would be the time complexity in this case, right? The time complexity is, again, as I've mentioned earlier, the time complexity in this case constant, so it does not depend. The runtime of an algorithm does not depend on the input size. So let's say that the input sizes, we are taking 10, 100, 1000, and 10,000, and we are running our algorithm. So we are running our function with these inputs. So in that case, and let's put that into the chart. So in that chart, as we can see, the runtime of an algorithm does not depend on the input size. Doesn't matter what is the input. So let's say 10, 100, 1000 or 10,000 in this case, the runtime of an algorithm won't change because it does not change depending on the input. So the time complexity in this case is of 1 or it's constant. Let's review another time complexity which is higher than constant, which is the log n. So in this case it's a logarithmic time complexity. So for that, let's review a scenario when we have a binary search. We are receiving an array, and when we are in our function binary search, we are receiving an array as an argument, and another one is target. So we need to find that target in that array. So for that, we are performing a binary search. The question that we should ask ourselves when we are calculating the time complexity is how many steps we have to make in the worst case scenario to get an answer. Again, I'm going to repeat that again. How many steps we have to make in the worst case scenario to get an answer. So for example, in this case, each time we perform a comparison, each time for a binary search, we halve the size of the problem. So let's say that our initial size of our problem is n. So we are in the first iteration, we are halving that to 2. So n divided by 2, then n divided by 4, n divided by 8 until we have 1. So in our case, let's say we have an array. So let's say that our input size of our array is 16, and we are finding a target in that array. So first what we do is we are dividing that to half, right? So we are getting 8 divided by 2, 4, and the 4 divided by 2 is 2, and 2 divided by 2 gives us 1. So how many steps, so in this case, right, how many times we should half out input in the worst case scenario? So how many steps we should make in order to get an answer? To simply say, so in this case, we are making 4 steps, right? So we are 4 times dividing. In the worst case scenario, we are 4 times dividing we are making 4 steps in order to get our answer. So what is to the power of what? To the power of what will give us 16, right? So log 216, which means that the 2 to the power of what will give us 16. 2 to the power of 4 gives us 16. So we take our time complexity, in this case log n, which means that the log 16 in our case, right, for this specific scenario. So if we run our function with the input sizes 10, again 100, 1000, and so on, and every time we are increasing that to tenfold, and we put that into chart, we can see that the dependency is indeed dependency of the input size, and the runtime of an algorithm is logarithmic. So the dependency is logarithmic in this case. So let's go to another one when the dependency is linear. So which means that the runtime of an algorithm will increase as we increase our input size. So they will increase linearly. So for that, let's review let's take an example of a linear search. Let's say that we have a function linear search where we are receiving an array, and we're receiving a target, and we need to find that target in that array. So for that, again, with the question that when we are calculating a time complexity, the question that we should ask ourselves is how many steps we have to make in the worst case scenario to get an answer. So in this case, how many steps we are making. So let's say that the size of an array is n, right? And let's say that our target is at the end of the array. So which means that in the worst case scenario, we have to look up for every element in our array. So which means that for the array with the size of 5, if our target is at the end of the array, we have to go through every element in the array. So the time complexity in this case would be, if the input size is 5, if the input size is 5, then the runtime also would be 5. So if the input size is 5, so we have to make 5 steps. If the input size is 50, then we have to make 50 steps. If input size is 100, then we have to make 100 steps. So which means that our dependency is linear. Now let's run our function with the input sizes 10, 100, 1000, and so for other inputs increasing every time tenfolds. So if we run our function, we can see that indeed our dependency on the runtime depends on the input size. The dependency is linear in this case. Next time complexity is n log n, or linear arithmetic time complexity. So for that, let's take an example of an array, and in this case we need to sort the array. We are going to use merge sort algorithm in order to sort this array. So what we are doing in the merge sort algorithm is, to put that in a simple terms, so what we do is we are dividing an array until, so for example, in this case, we are dividing to 2 parts, and for each part we are again dividing those to smaller parts and so on, and then we started to merge. So for example, let's say that we have divided that to our array to the 38, 27, and 43. Now we start to merge them, and when we start to merge, we are comparing the first element in each. So for example, we are comparing 38 and the 27, so whichever is the lowest. So first we are adding to our result 27, then we are comparing 38 with the 43, and we are first adding 38, and then we are adding 43. Now these two parts are the merged parts that we have. They are sorted. Now again, what we do is we are merging those sorted parts together. So for example, we are merging 27, 38, and 43, and the 3, 9, 10, 82, and then now we are merging them into our final result, which is, again, we are comparing 3 with the 27. So first we are adding 3. Again, these two parts, 27, starting with the 27, 38, and 43, and the 3, 9, 10, 82, they are sorted already. So what we do is we are going over our two sorted parts, and we are merging them into one sorted array to our final result. So we are comparing 3 with the 27. So we are comparing 3 with the 27, and we are adding first 3. Then we are going to the next element. We are comparing 9 with the 27, we are adding 9. Then we are comparing 10 with the 27, we are adding 10, and so on. So that we are merging our array. So what we do actually here, we do two operations. The first operation is that we are recursively calling and splitting our array to half. So first we are halving our array, then we start then after halving our array, then we start to merge them. So for example, in this case, let's say that if the size of our array is 16, so we are halving that to 8, so we are halving that to 2, we are halving that to 4, and to 2, and after that we are starting to, after halving our array, we are starting to merge our array. So for each recursive call that we are making, we are iterating through all elements, and we are merging them. So for example, in this case, let's take an example when we have this scenario, right? So how many times we are halving our array. In this case, we are halving our array twice, and we are halving our array 3 times, and we are going 3 times over our array to merge them, which means that for every half that we are making, we are also going to over our array at least over our array once to merge them. So which means that our final time complexity would be log n, because we are halving our array, and for each halving that we are doing, we have to merge them back. So because we are merging them back, to our time complexity would be log n multiplied by n, linear arithmetic time complexity. So if we look at the code in our merge sort, so what we do is we are receiving an array. First thing that we do, we are sorting our So what we do is that we are recursively calling, and we are for the left hand, for the left side, and for the right side. And after we split our array into 2 halves, then we are starting to merge them. If we run this algorithm, if we run this function for the input sizes 10, 100, 1000, 2000, and so on, so we can see that in our graph, the dependency of the runtime of an algorithm to the input size is linear arithmetic. So which means that it's slightly worse than our linear time complexity, but it's better than the better than the quadratic time complexity. So now let's go to the next one. When our time complexity is n square, so it's worse than n log n time complexity. So for that, let's take an example of the bubble sort. So for the bubble sort, and the question again, we should ask ourselves that how many steps we have to make in the worst case scenario to get an answer. In this case, how many steps we are making. So for the bubble sort, what we do is for every element, we will go over our array once. So starting from the beginning of the array. So which means that if our input size is 5, so for each element we will go to 5 times. So which means that 5 multiplied by 5 gives us 25. If the input size is, let's say, 10, then in that case we have to make 100 steps. 100, then we have to make 1,000, we have to make 10,000, and so on. So it leads us to the time complexity of n squared, right, or the quadratic time complexity. Again, we are taking the input sizes 50, 100, 200, 300, and every time we are increasing that by 100. And if we run our function with this input size, we can see in our chart that the dependency of a runtime to the input size is indeed quadratic. So now let's go to the next one. Next one is the cubic runtime, so n to the power of 3, so cubic runtime. So for that, let's take an example of a Floyd-Warshall algorithm. So Floyd-Warshall algorithm, in a nutshell, it's an algorithm to find the shortest distance between all nodes. So for example, let's say that we have 4 nodes, A, B, C, D, and we need to find the shortest path. So we have, let's say that the path from A to B, from A to C, so we have several paths from how to go from A to B, from A to C, and A to D, and so on. So what we need to do is we need to find the shortest path, how to go from each node to another node. So for example, from A to B, and from vice versa, from B to A, and so on. So for that, we are using a Floyd-Warshall algorithm. So what we basically do is here, let's say that from going A to D, right? So from A to D, we can go from A, so we can go directly from A to D, right? Or we can go from A to D from B, from C, and so on. So we are considering all these cases, and for that we are running 3 for loops. So for example, the I and the J, let's say that the going from I and J is going from A to D, right? And the K is that how we are going from A to D is, are we going from node B, or we are going from node C. So for that we are running 3 for loops. And the time complexity in this case, what will be the time complexity? Again, we are asking ourselves the same question: how many steps we have to make in the worst case scenario to get an answer? In this case, the number of the steps that we are going to make. If we have 5 nodes, so which means that we have to make 125 steps, because we have to make the, so we have 3 for loops, and for each one we are starting from the beginning, so which means that the 5 multiplied by 5 multiplied by 5 gives us 125. If we have 10 nodes, so which means that we have to make, in the worst case scenario, 1,000 steps. We have to make 1,000 steps in order to get an answer. And in this case, so it will lead us to the n to the power of 3, so which means that the cubic time complexity. Again, we are running with the input sizes with the 10, 15, 20, 25, 30, and for the let's say that for 10 nodes, for the 10 nodes, for the 15 nodes, 20 nodes, and so on. So as we can see here, the dependency of the runtime of an algorithm to the input size is cubic. It's worse than our previous time complexity, which is quadratic and square. So now let's go to the next one. Now the higher time complexities, which are the exponential time complexities. We have 2 here, to the power of n, or and another one, n to the power of n, which is worse than the to the power of n. And let's take for that very simple example. Let's take an example of a Fibonacci sequence. Let's say that we have a Fibonacci sequence. If you are not familiar with that, Fibonacci sequence is a sequence when the sum of the when the element is the sum of the previous 2 elements. So for example, 3 is the sum of the 1 and 2, and the 5 is the sum of the 2 and 3, and let's say that the next element would be 8 because it's the sum of the 3 and 5, and so on. So what we do in this case to solve a Fibonacci sequence problem, so we are recursively calling, so we have a function Fibonacci, and we need to find the n, which means that the Fibonacci number at the, let's say, at position 5, right? In this case, at position 5, so we have 8, right? Because 1, 2, 3, 5, and the next element would be, 5th element would be 8. So we need to return that. So for that, what we are doing here, we are recursively calling for the, so we are basically breaking down to our Fibonacci sequence. So what would be the at the, let's say that the n is equals to 4, right? So for 4, what would be the number? For the 4, the number would be that the sum of 3 and 4, right? So for example, let's say that for the 5, it would be the sum of Fibonacci of 4 and the sum of Fibonacci of 3. So we are running that for 4 and the 3. And for 4, we are again recursively calling, and that would be sum of 2 and 3 and the 2. And for 2 is we have only one number, so we are returning 1. So the same again for the when the Fibonacci is equals to 3, we are recursively calling to 2, and for the 2, the Fibonacci, we are recursively calling Fibonacci 1, and we are returning 1. So again, in this case, right, so how many steps, again, the question we should ask ourselves, how many steps we are making in order to, in the worst case scenario, to get our answer. So for example, let's say that our Fibonacci sequence is not 5, it's 20. For 20, we need to call at least twice, right? We are calling for the 19 and 20. For the 19 and 20, we are in turn, for the 19 and 20, we are calling for the 18 and the 17, and for the 18, we are calling for the 17 and the 16. So what it means? It means that every time for every next step, we are doubling whatever was the previous step. So for example, for the 20, we are calling only 2 functions, right? 19 and the 18. So for the next step, which means that for 19 and 18, we are going to call the function 4 times, because for the 18, 17, 17, and 16. And for the next step, which is the third step, we are going to call for the 18, 17, and the 17 and the 16. So which means that we are going to call 4 times. So every time when we are going one step further, we are exponentially increasing the number of the calls. So in this case, the time complexity for the Fibonacci sequence would be to the power of n, because for the n calls, for the n input, we are going to make every time again we are exponentially will increase we are going to exponentially increase the number of the calls. So the time complexity in this case would be to the power of n. So, and the last one that we are going to review today is factorial time complexity. For the factorial time complexity, let's take an example of a permutations. Let's say that we need to generate all possible permutations. Let's say we have an input side, we have an input array of 1, 2, 3, and for that we are generating all possible permutations, which is 1, 2, 3 in this case, 1, 3, 2, 2, 3, 1, and so on. So for that, what we do is let's break down step by step. For the first position, right? For the first choice, how many choices we can make? So we can make 3 choices. We can choose either 1, we can choose either 2, or we can choose 3, right? So for the second position, how many choices we can make? So we already used we have now 2 elements because we used already 1 element in the first position. So in the second we have 2 choices. We can either choose 2 or we can choose 3, right? So and for the third position, so how many choices we can make? For the third position, we can make only 1 choice, which leads us that our time complexity in this case would be 3 multiplied, because we can make 3 choices at the first step, right? So at the second step, we can make 2 choices, and at last step, we can make 1 choice, which is that the n multiplied by n minus 1 multiplied by n minus 2, and so on. So which gives us factorial time complexity. So if we look at the code here, so what we do is we are creating an array result, which we are returning, and we are using a backtracking function here, backtracking algorithm. So we are passing our nums, we are passing an empty array, which will be the temporary list that we are adding to our result, and we are passing result. So what we do is if our temp list, right, if it equals to the size of our array, then we are adding that to our result. If not, then what we do is we are going and we are recursively calling and adding our so for example, let's say that if num already is in the temp list, we are skipping that because we should not add the number that we have already added. If not, then we are adding to our array, and we are recursively calling our backtrack function, and we are as we backtrack, we are also removing from our temp list, we are removing the elements of the branch from where we are backtracking. So to sum up our time complexities, so our lowest time complexity is constant. So when the runtime of an algorithm does not depend on the input size. So the higher one is the log n time complexity. The next one is that we have reviewed is the linear time complexity. The next one is n log n, and the next one is quadratic time complexity. Now after that it comes cubic time complexity, and then we have exponential time complexities, and to the power of n, or n to the power of n. N to the power of n, it grows faster than to the power of n. And the last one that we have reviewed today is a factorial time complexities. We also have a space complexity. It's calculated exactly the same. It's basically the space complexity, if to sum up how the space grows depending how the demand for the space, right? How much space do we need? It grows depending on the input. Let's say that for example, and the calculation is the same, right? So if we have an algorithm that requires us to create an array, and it will grow, that will create an array, and then in that case the time complexity of that would be of n, because we are creating an array, we are storing our as many elements as our input is. Let's say that for an array we are creating another array where we are going to store a temporary results. So for that, the space complexity of that would be of n. Or let's say that for some other reason we need to create a 2-dimensional array. So for that, which with the size of n to n, so which means that in that case our time complexity would be n squared, because we are creating an extra space that grows quadratic to our input. Okay, that's it for today. Hope you like my content. If you like it, please hit the like button and subscribe my channel. See you next time. Bye.